Born in the 1980s, the microwave landing system was intended to be a more accurate replacement for the ILS system, serving the aviation industry worldwide at the time. With the ability to support curved approaches and even aircraft-specific approaches, it was far more advanced than ILS and was supposed to be the new, safer advancement in instrument approaches. This worked well for airports in Europe and Asia who adopted the new system. However, the innovation never really took off in North America, and the FAA cut off funding by 1994. North America then turned their attention to the up-and-coming GPS system and considered potentially integrating it into their approaches, which we now know as differential GPS. The MLS itself was designed to have a larger coverage area and more channels than ILS, meaning it could handle more aircraft coming from a wide range of angles on the same approach. The MLS was also less susceptible to the dangerous ground interference that the ILS was plagued with. It remained unaffected by the presence of cars or aircraft in its vicinity, while the ILS experienced a curving of its beam when met with the same situation, affecting the accuracy and dependability of the ILS approach. In the end, however, it was timing that killed the MLS system, and many airports chose to instead fund the conversion to GPS. Only a handful of airports still have functioning MLS systems. In its most basic form, the MLS system is a precision approach device, providing ground-to-air communication to a wide coverage area. Similarly to the concept of ILS, this communication includes aircraft positioning and distance from the runway selected. Its basic functions, being location and distance, are run by two main pieces known as the protractor component and the range-finding component. These components are each divided into smaller subsystems which allow them to complete their key functions. The protractor component functions almost exactly as you'd expect. The component acts as a sort of protractor to locate the angle and height of the approaching aircraft. It completes these functions using two channels 300 kHz apart. These two channels are known as the azimuth and elevation beams. The azimuth beam, which identifies the aircraft's bearing to the station, uses a horizontally sweeping beam providing coverage for aircraft on approach as well as aircraft conducting an overshoot. The wide sweep area of this beam allows for aircraft to join the approach from whatever angle suits their needs or the needs of the controllers. Working alongside the azimuth as the other half of the protractor is the elevation beam. This uses a vertically sweeping beam to identify the aircraft's elevation, starting at about 1 degree above the horizon. The other significant component of the MLS is the range-finding component. This consists of a precision DME, which transmits on a separate frequency, providing the pilot accurate distance information on their approach. These three essential pieces of information, bearing, height, and distance, are then processed and displayed by the onboard equipment. This onboard equipment consists of at least one MLS antenna, a transponder capable of interrogating the precision DME, a display, and some sort of receiver. This typically comes in the form of a multi-mode receiver. The MMR is capable of receiving signals from an assorted handful of approach types, and is the most efficient use of space and weight for most aircraft. This receiver displays valuable data to the pilot and allows the pilot to adjust their approach to best fit the landing requirements for their aircraft, typically for short takeoff landing aircrafts and other unconventional landing types. This information can also be sent to the aircraft's automation, given that the automation is flying the approach.
As was mentioned earlier, the microwave landing system works on two main channels, which are spaced 300 kHz apart and are often called the protractor components. The protractor components consist of two main beams, the azimuth and elevation beams, but more complex systems may also have a back azimuth beam as well. In addition to an extra beam, the ranges of all beams vary with the advancement of a particular system. Again, a more complex system means a greater range. As was also mentioned earlier, the final piece of the 3D puzzle provided by the microwave landing system is the range-finding component, supplied by distance measuring equipment, or DME. This 3D picture allows for a more accurate reading of aircraft position and enables the pilot to customize their approach path. The microwave landing system also does not need the specifically flat terrain within a certain distance in front of the beams, as the instrument landing system does, so it can be utilized in many more locations. The azimuth beam scans for aircraft horizontally and typically reaches plus or minus 40 degrees either side of the runway centerline and 20 degrees upward in elevation beginning from 8 feet above the runway surface. The beam also has a range of about 20 nautical miles. Some of the more complicated systems, as described on the previous slide, have a greater coverage and can reach up to 60 degrees horizontally and 30 degrees vertically. The elevation beam scans for aircraft vertically and typically reaches up to 15 degrees above the runway, beginning from 8 feet above the runway surface, and horizontally plus or minus 40 degrees either side of the runway centerline. The beam has a range of about 20 nautical miles and a minimum vertical angle of about 0.9 or 1 degrees upwards, and also reaches an altitude of about 2,000 feet above the ground. This angle in particular is superior to ILS because it allows for far more accurate low-altitude coverage on approach to land, as well as during a missed approach, which will be discussed next. The back azimuth beam is very important as it covers low altitudes, providing guidance for aircraft executing a missed approach and rejoining a landing pattern or exiting the area. Because the microwave landing system does not require flat terrain near the beams, it is possible there may be obstacles that may be avoided, as well as other traffic making their own approaches into the airport. With the system, everyone's position can be taken into account and that avoidance can be accomplished. The back azimuth beam reaches horizontally about plus or minus 20 degrees from either side of the runway centerline and reaches vertically about 15 degrees up, beginning from 8 feet above the runway surface. The beam also reaches an altitude of about 5,000 feet above the ground and has a range of about 5 nautical miles. Though the flare angle beam was designed and standardized, it was never actually integrated into the microwave landing system. Its purpose was to provide a reading of an appropriate flare elevation during the final landing process, specifically during automatic flare and landing procedures. The flare beam was supposed to reach vertically at an angle of about 8 degrees, beginning from 8 feet above the runway surface. It was also supposed to have a range of 5 nautical miles and reach an altitude of around 4,300 feet above the ground. In terms of the most basic microwave landing system configuration, the azimuth beam antenna is typically about 1,000 feet from the end of the runway, in line with the runway centerline, and placed with the distance measuring equipment. The elevation beam antenna is usually about 400 feet from the edge of the runway and closer to the end of the runway opposite to the azimuth beam antenna and DME. In more complex systems, the back azimuth beam antenna is about the same distance from the end of the runway as the azimuth antenna, but the two are placed at opposite ends. If it were implemented, the flare beam antenna would have been placed about the same distance from the side of the runway as the elevation beam antenna, but closer to the middle of the runway. These figures are, of course, simply standard ones, but because terrain and obstacles are not an issue for the beams, variations in placement and configuration are certainly possible.
When the microwave landing system was originally designed, it was designed to take over for the instrument landing system at airports. Thanks to the microwave landing system, aircraft can approach and land at airports with greater precision than when using the instrument landing system. This is because the microwave landing system does not suffer from electromagnetic interference, as well as other elemental interference. The microwave landing system is invulnerable to elemental interference because of the frequency range that it operates in. The microwave landing system operates in the super high frequency range. Since it was designed differently, the microwave landing system allows airports to have flexible approach paths that were not previously possible when using the instrument landing system. This means that different aircraft can approach the airport from different locations and have different approach paths. The microwave landing system has advantages over the instrument landing system. One of the advantages to the microwave landing system is making aircraft's approaches more efficient. For example, short takeoff and landing aircraft, or STOL aircraft for short, can now approach the airport at a greater approach angle than other aircraft, making their approach to the airport more efficient. However, in order for the microwave landing system to have flexible approach paths, it has to operate at higher frequencies than the instrument landing system. The operational frequencies that the microwave landing system utilized are from 5031 MHz to 5090.7 MHz, and the channels are spaced by 30 kHz. The microwave landing system has a total of 200 channels available to operate on worldwide. This is made possible by the 300 kHz of spacing between channels and the 59.7 MHz of bandwidth that have been allocated to the use of the microwave landing system. However, this being said, you cannot have 200 channels operating at any specific airport at any given time. This is made evident in a city like New York because there are 3 major airports there, all of which utilize various landing systems. It's for this reason that the increase in number of channels is important, because it alleviates the congestion on the number of available channels. The way it does this is by increasing the number of channels that are available to be used. When you look at a system like the ILS, there's only 40 channels available. And with how far radio waves can travel, it greatly limits the number of channels that are available when you have 3 airports. So to get around this, they've increased the number and given specific airports specific channels that they can operate on. When you look at the chart that's on the slide, you will notice that there's a lot of information that's given there. So let's look at it for a moment. Let's start with the channel pairing column. And that column is broken up into 4 sections. The DME channel number, the VHF frequency in megahertz. Then you're given the MLS angle frequency in megahertz as well. And then finally, under that heading, you're given what channel number it is for the MLS system. And then the other column that is provided is all the DME parameters, or distance measuring equipment parameters, for each channel. So first, we will look at the interrogation side of the DME, which you're given, again, 2 columns. You're given the frequencies and then the pulse codes. So when you look at the frequencies, those are all given in megahertz, and the pulse codes are given in microseconds. And then finally we have the reply column under the distance measuring equipment parameters, which are again given under 2 subcolumns, which are the frequency in megahertz for the aircraft to reply on, and the pulse code that the aircraft are to reply on. All this information comes from Table A12 of the FAA Standards 022 document that you can either find in that document on the FAA website, or you can find in the full write-up of our report under the number of available channels. What does a pilot see when conducting an approach using the microwave landing system? Well, you would see the exact same thing as you would see when conducting an approach using the instrument landing system or the global positioning system approach. The reason for this is that they use the same instrument. So in order to not have conflicting information showing up and confusing either the pilot or the instrument, there's a source selector that allows you to select which system you want to use in order to conduct your approach. The advantage of the microwave landing system over the instrument landing system is it allows you to conduct an approach from anywhere at the airport. The reason this is an advantage is it has the potential to make approaches into the airport far more efficient. This is evident when you look at, for example, a STOL aircraft like we talked about in the previous slide. But how does that show up on an instrument? Well, let's look at the image on the screen, because that is the instrument you would see for conducting the approach. And as you can see, there are two bars. There's a horizontal bar and there's a vertical bar. Let's start with the vertical bar. The vertical bar shows you your position left or right of your desired path to the airport, or rather to the runway. And the vertical bar shows you your desired position in relation to the glide slope that you have selected to use. So the advantage of the microwave landing system is that you could be approaching from higher or lower depending on what your aircraft needs are. But no matter what your aircraft needs are, it will show up the exact same on this instrument. So what this instrument is showing us right now, for example, is that our aircraft is slightly below our desired glide path and slightly too far to the right. So then you would correct to get those where those bars are crossing right in the center of that circle. And that is where your ideal position would be for that approach.
There are two main types of transitions in the MLS system. The first one is the angle transition. It is the most important signal, and it incorporates approach azimuth, high rate approach azimuth, back azimuth, approach elevation, flare, and basic data transmissions. The second type of transmission is a pure data transmission. It includes any supplemental information such as runway and meteorological conditions that can be fit around the previous transmissions. The MLS transition is modulated using DPSK or differential phase shift keying and continuous waveform signal modulation. There's an allowed variance of plus or minus 10 kilohertz overall and plus or minus 50 hertz in any 1 second period. DPSK modulation is a change in the phase of the carrier wave. Each carrier wave has a finite number of phases that it can be transformed into. Each phase encodes an equal amount of bits through binary coding. These bit patterns form a symbol that represents a different phase, so the phase represents a symbol. In DPSK, the phase symbol is determined in reference to the last symbol sent, so the current signal is compared to the previous symbol. This system is simpler than other types of phase modulation, but is more prone to demodulation errors. Its bit rate is 15.275 kHz and its bit rate is 64 microseconds. Logic 0 has no phase transition and Logic 1 has a phase transition in accordance to binary systems. The second type of modulation used in MLS is continuous waveform or CW modulation. In this system, a continuous sine wave is turned on and off. The information is carried in the differences in timings of the on and off in the signal, aka Morse code. The CW signal must be in 150 kHz bandwidth centered 850 kHz or more from its assigned frequency. And in this system, it does use Morse code to transmit its data. The angle transmission is made up of three main components: the preamble, sector signals, and an angle scan. The preamble consists of the CW carrier wave acquisition, so basically identifying the carrier wave, the receiver synchronization code, which is used to make sure that this signal doesn't interfere with any other signal being sent out, and a function identification, which is the continuous waveform Morse code identification. This is used for both angle and data transmissions. In the sector signals, this consists of a Morse code identifier starting with a M or mic, antenna selection, and the test signals being sent out to verify receiver validity. In the angle scan, the beam moves back and forth across the sky that is interpreted by the cockpit instruments and gives guidance. In the data transmission, it also is consisted of two parts, the preamble and then the actual transmission of the data. In the preamble, it functions the exact same way as it does in the angle transmission, and then the data actually transmitted is just transmitted along using DPSK modulation. MLS transitions use a TDM or time division multiplexing cycle in order to ensure accuracy and make sure that none of the component parts are stepped over by other parts of the signal. The transmissions follow a preset cycle pattern using two sequences with open time in between to prevent signal distortion, and data can be transmitted during any open time between the sequences. There are two types of angle transmissions. The first one is the normal approach azimuth guidance, and the second one is the high rate approach azimuth guidance. The high rate is used for antennas with a beam width that's greater than 2 degrees. If you think about the SSR main lobe, so the wider the beam width means that there's more area covered by the beam in the same amount of time. Both types have a two-sequence pattern that they use to transmit their guidance data, and both can utilize an out-of-coverage indication, which is an OCI, which will cause an error in the system if the aircraft is not within the coverage zone of the MLS beam. The normal approach azimuth sequence is made up of a few component parts, including approach elevation, flare, approach azimuth, and back azimuth, and also some time open for data transmissions. Data words can be transmitted during any time in the transmission that is open, and the maximum transmission duration is 134 milliseconds. The approach azimuth transmission lasts 15.9 milliseconds, and the approach elevation transmission lasts 5.6 milliseconds. And the flare guidance was designed but never implemented. The high weight approach azimuth sequence includes 4 component parts and also data transmission sequences. Approach elevation, high weight approach azimuth, and back azimuth. The longer time duration of the signal is because there's more data to be transmitted, so less time is available for supplemental data transmission. The maximum transmission duration is still 134 milliseconds. Basic data words can be transmitted still during any open time in the transmission, and if back azimuth is provided, data words can only be transmitted during the time slot of Note 2, as is seen in the slide. The approach azimuth transmission lasts 11.9 milliseconds, and the approach elevation transmission lasts 5.6 milliseconds.